All right, so this is the last chapter for Chem 262. We're going to talk a lot about aromatic compounds and what it means to be an aromatic compound. Does anybody know the old-fashioned definition for how they determine whether or not something was aromatic? It's smelly, right? You think about aromatic things in your house, they tend to be smelly, right? So the old definition was pretty generic. The old definition just simply meant that it was smelly. It could be good smelly, it could be bad smelly. They just described all of smelly compounds as aromatic. The reality is this is not even close to true. In fact, a lot of aldehydes smell, a lot of esters smell. There's a lot of different functional groups that smell besides just aromatic functional groups, right? So it's not really a very good definition. So it's been updated to a more modern definition. And the modern definition really rolls off the tongue. It's a planar ring system with 4n plus 2 pi electrons that are delocalized. Around the ring. So you can tell they definitely added a new layer of understanding to what it means to be aromatic. We'll go back and we'll talk about what that 4n plus 2 really means. That's called Huckel's rule, but it's used to predict whether or not a molecule will be aromatic. Yep?
So with our modern definition, aromatic compounds are smelly?
Some of them are, some really aren't. So if you take, for example, one of the larger acenes, so we saw acenes yesterday in class where we were talking about color, those really don't have a smell, especially once they get large enough because they don't really have much vapor pressure. So it just completely depends on the aromatic system. Smaller acenes definitely stink. In fact, how many of you have ever smelled mothballs? Yeah, mothballs usually have naphthalene in them. They inhibit the life cycle of moth larvae. So sometimes they are quite smelly. It just depends on a lot of different properties. Yep.
So then what, like for instance, purines that would technically fall into this aromatic system?
Yeah, so
what actually causes for us to actually smell this?
That's a good question. Usually that has to do more with vapor pressure than anything, and then just the receptors that we have in our nose. That gets into more biology than organic chemistry. So I'm just going to kind of stay hands off with that. But you can ask your bio teachers that. All right. So now we have to jump into nomenclature. And naming these is kind of non-trivial. However, the first thing we need to do is talk about generic prefixes. And if we have a generic benzene ring that's mono-substituted, it's nice and simple. So for example, if we have a methyl group in that R position, we could call it methylbenzene. We could have an ethyl group on there. We could call it ethylbenzene. We don't need to talk about it using any special fancy prefixes. However, let's take another example. Let's say we have a di-substituted aromatic ring, where we've got A and B opposite of one another. And I'm just using A and B as generic placeholders, versus them being kind of at the 12 o'clock to, what would that be, 4 o'clock position, versus our 12 o'clock and kind of like 2 o'clock position. These are all di-substituted aromatic rings, right? But they're not at all the same. How are they related? They're all constitutional isomers. They have very, very different physical properties, but we need to be able to describe the relationship to one another. All right, what do you think we could do in order to describe the placement of A and B in this system? So you're reading ahead. What did we normally do when we tried to identify relative positioning of substituents? We number it. So what you could do for this one is you could number and you could go 1, 2, 3, 4. So you could call this 1, 4 and then name your substituents coming off. However, sometimes that gets to be a bit much because these systems are so common. What this is often referred to as is para-substituted. And often the abbreviation is just a P, and then you have P dash whatever your molecule name is. The next one is 1,3 disubstituted, and this is meta, and that has the abbreviation M. So if you have something that's meta-substituted, like meta-chloroperoxybenzoic acid, you use an M dash whatever, right? So in this case, meta means it's just 1,3 positioning of these two substituents. And then last but not least, we've got 1, 2, and then this is called ortho, and it has the abbreviation O. Really, you can use them interchangeably, but you should know how to interpret what para means if they don't use the 1, 4 numbering system. Yep.
So what about, like, so if it's a methyl group and an ethyl group, is it like ortho, ethyl, benzene? Or?
Yeah, so we'll come back and we'll talk about the naming. It gets even more complicated than that. So we'll leave that as is for now. One thing people will often ask me is they'll say, what about tri-substituted rings? What about tetra-substituted rings? What about hexa-substituted rings? Once you get past 2, then generally you stick with the numbering system. It's just a lot easier to do the numbering for more complicated systems. But ortho, para, and meta, these systems are still used in a lot of chemical naming, so we need to know both techniques for naming. All right, so that gets us into these older names that have stuck. All right, and unfortunately, when the IUPAC committee got together to come up with this standardized system, there were a lot of people in the room that said, I don't want to rename all of these molecules I've used for the past 50 years. So the IUPAC committee basically folded and they're like, fine, you win, you can use your old names. So a lot of these older names have persisted. So for example, this compound, most sophomore level organic chemistry students would look at this and they'd say this is methylbenzene, right? Which isn't incorrect. You can definitely call it methylbenzene. However, most chemists, instead of calling it methylbenzene, stick with the old name, which is called toluene. So toluene is synonymous with methylbenzene. All right, the next one is kind of similar. Most sophomore level chemistry students would call this hydroxybenzene. But more chemists would prefer to call this phenol, the older name. So it's not that one's more right than the other. And then we can do another one. A lot of chemists might call this, Methoxy Benzene. However, if you're in the chemistry field, typically you refer to this as anisole. So I do want you to know both naming systems and preferentially use the one in blue just simply because that's what more chemists use. They prefer the older naming system. All right, there's a few more we got to cover. Some of these are pretty intuitive. What would this one be called? It's half benzene, half carboxylic acid, benzoic acid, absolutely. All right, so benzoic acid, people just call it that. It doesn't really have two naming systems. Some people, although not many, would call this benzyl methyl ketone. However, that just sounds really, really weird, doesn't flow very well. So almost everybody calls this acetophenone. My favorite was one year I had a student that kept on calling it acetophenone. It sounded very Italian. But acetophenone. Then this one, some people might call vinyl benzene. However, it's not really commonly used. In fact, most people just simply call this styrene. Does anybody know what styrene's used in? It's used to make polystyrene, so styrofoam's made out of polystyrene. So that's a common monomer in the plastics industry. All right, the next one is the aldehyde. Yep. With an aldehyde, it's benzaldehyde. Next one is with an amine. Some people might call this aminobenzene, but again, I just don't like the sound of that. Most people call this aniline. Aniline is the old school name that just stuck for aminobenzene. And then we've got one that looks like toluene, where we've got a CH3 on each side. So it's di-substituted. What do you think the positioning is for this one? Para. So this is called para-xylene. So it's not super intuitive, but it's the old school name. There's also orthoxylene and metaxylene as well. It depends on the positioning of those two methyl groups. So all 9 of these are commonly used parent names. So these are common parents used in naming. So you should know all 9 of these roots in order to name molecules appropriately. So this does require a little bit of work, but usually after you do it a handful of times, it just kind of sticks in your brain. You'd be surprised how fast it'll stick in your brain. But if you are struggling, you can always make flashcards. That's a good way of kind of drilling it into your brain pretty quickly. All right, so let's see these parents used in action, and I'm going to start out with my favorite one. So typically when you're given an unknown structure that contains an aromatic ring like benzene, your goal is to find one of those 9 parents and then everything else treat as a substituent. So let's do one of these. It's going to be tetrasubstituted. All right, so what's the parent here? Toluene, right? So if we think about the parent, the only one of those 9 compounds that we have is going to be the toluene that I'm kind of tracing in red right there. And then if we go over here, we've got these NO2 groups. What are they referred to as? Nitro groups, right? So NO2 is always going to be a nitro group. All right, so now we need to number it, right? So when we go to number, you always want to try numbering starting at the carbon that's substituted for your parent. So we could go 1, 2, 3, 4, 5, 6. So what do you think the name for this will be? Check with your neighbor and see if you agree. You don't do directors if it's more than di-substituted. You only do ortho, para, and meta if you only have 2 things, right? So this is more complicated. We got to use a numbering system. All right, give me a thumbs up if you think you got it. Give me a thumbs down if you're lost. All right, so let's walk through this, right? So with any naming convention, we need to first start out numbering and then list our placement of substituents. So in this case, we've got nitro groups coming off the 2, 4, and 6 position. So we could go ahead and we could say this would be 2, 4, 6. And because we've got 3 nitro groups, we need to have tri, right? And then we need our parent, which is toluene. Does anybody know what most people call this? TNT, I'm dynamite, right? Does anybody know that song? Yeah. So the thing that always bugged me with AC/DC's song where he goes, "I'm TNT, I'm dynamite," is dynamite is not TNT. Those are two completely different things. TNT is just TNT. He should have just said, "I'm TNT," and left it at that. But anyways, that's where they got the TNT name from. All right, let's try another one. So kind of side story on TNT, the more nitro groups you have, the more explosive compounds in organic chemistry tend to be. What chemists often look at when they look at the potential for an organic compound to explode is the carbon to nitrogen ratio. And once that nitrogen ratio starts getting high enough, things get to be a little bit more exciting. Yep.
So if we have a meta substituted benzene ring, which carbons, which one should we start the numbering from?
So if you're using the ortho, para, or meta system for a di-substituted ring, you don't do numbering because it's already implied.
There's other stuff on it, like if it was, instead of toluene, or I guess there's a para ones.
Yeah, that's a good question. So you can't use ortho, para, and meta if you have more than two substituents. You can only use ortho, para, and meta if you only have a di-substituted aromatic system, right? If you've got more than that, you have to go with the numbering system. And just like with any numbering system, you want to minimize numbering and minimize your alphabetization if needed.
So if it was xylene, it would just be called xylene. It would be called something xylene, and be whatever the substituents were, and then xylene.
So with xylene, you could have orthoxylene, metaxylene, or paraxylene. But by definition, xylene's di-substituted, so you don't need the numbers.
Well, I mean, if there were two bromines coming off of the paraxylene.
Then it wouldn't. That's a good question. So with xylene, I'd have to look that up. Yeah, I'll look that up and try to get back to you. Good question, though. All right, so let's try this one, and then I'll actually give you another one underneath. So let's try doing both of these and then check with your neighbor. All right, so let's do the top one and identify the parent first. What's the parent for the top molecule? Styrene, right? So we can go ahead and we can say, all right, I'm just going to trace around my parent, which we know is styrene. And if we go to number, we want a number going clockwise or counterclockwise? Clockwise. That way we minimize numbering. So we go 1, 2, 3, 4, 5, 6. Can we use ortho, para, or meta for this one? No, because it's got too much going on. So we've got a bromine coming off of carbon 2, a chlorine coming off of carbon 4. Which one should we list first and why? Bromine, because it's slower in the alphabet. So we could go ahead and we could say, all right, this is going to be 2 bromo, because bromine's lower in the alphabet. And then we do 4 chloro, styrene. All right. All right, for the bottom one, what's the parent? Benzene. So benzene is the parent if you can't identify another parent out of that 9-carbon set. So we can go ahead and number this one. Do we want to number starting at the bromine substituent or the ethyl substituent? Bromine. Minimize the alphabet in this case. And do we want to go clockwise or counterclockwise? We want to go clockwise. That way we minimize numbering, right? If we go counterclockwise, it'd be 1, 5. That's not as good as 1, 2. Yep. Yeah, so let's do both, right? So let's do the numbering one first. So if we do the numbering one, we could go 1 bromo, 2 ethyl benzene. Or what we could do is we could call this ortho bromo ethyl benzene. Either one would work. However, if you use this lower one, make sure that you still alphabetize your substituents. IUPAC's really firm about trying to keep that order intact. Yep, great question. Does that make sense? All right. So let's take a look at a little bit about these aromatic systems and ask why they're so special. So what makes aromatic molecules special? And there's a few things that people immediately noticed with aromatic systems. The first is, let's say you have benzene, right? And you react benzene with elemental bromine. First thing people immediately noticed was that nothing happens. Whereas if we had cyclohexene and we react it with bromine, we could get an addition reaction that we saw kind of at the beginning of the term, where you'd have one bromine as a wedge, the other one as a dash, and you would end up with a mixture of enantiomers. So that's telling us immediately that these double bonds in our aromatic system don't have the same reactivity as normal alkenes. Why do you think that is? Resonance, right? So if we think about this double bond here, is it really a true double bond?
No.
What's the bond order?
1.3.
It's going to be about a bond and a half, right? So it's halfway in between a single bond and a double bond. Therefore, it doesn't do the same chemistry as alkenes. So that was one thing that people immediately noticed. The other thing people noticed was if you try to hydrogenate these, you get some odd results. So let's take this one, strange observation. Whoops. And what was originally done was a study where they took cyclohexene and they tried to hydrogenate it to cyclohexane. What reagent would we need to accomplish this? H2. And usually it's palladium on carbon, something like that. You can have platinum or palladium, it doesn't really matter. And when they did this experiment, they actually did it in a calorimeter. So they were able to measure the heat produced or absorbed during the reaction. And what they found was that the enthalpy, the standard enthalpy for this reaction, is about negative 120 kilojoules per mole. So they measured that pretty carefully. And then what they did was they took benzene and did a really similar experiment. However, they couldn't really use the same catalyst system. They had to switch over to a special nickel catalyst. And then they had to use 3 times as much hydrogen because we're trying to reduce 3 of those pi bonds, right? In either situation, you can reduce this to cyclohexane. First thing they immediately noticed was that it required really, really high pressure to accomplish this. In fact, most chemistry labs aren't equipped to do this sort of hydrogenation because you need specialized equipment in order to do it. So looking at the example above, what would you expect the standard enthalpy to be for hydrogenation of benzene? You'd expect it to be multiplied by 3, right? So you'd expect it to be negative 360, give or take. However, what they found was that the standard enthalpy for this reduction was negative 208 kilojoules per mole, not the expected negative 360. Oh, so what does that tell you about benzene? Does it want to be reduced? We've got a few clues. One is we can tell based on the fact that we had to change catalyst and increase the pressure, it does not want to be reduced. That and it's releasing less heat energy, meaning it really doesn't want to do that reaction, right? Yep.
Oh, and it's not a full double bond, it's not releasing as much energy when it's supposed to, right?
Yeah, so even with that factored in, the expected one was actually like negative 366. It's still not matching up with the theory. So what they were doing is trying to ask themselves what was going on with this, and they said that there must be some sort of hidden stabilization energy. and they can measure that stabilization energy to be approximately 152 kilojoules per mole of stabilization, and they call that stabilization aromatic stabilization. The weird thing with this is not all aromatic molecules are equivalent. It's kind of this series of grays. Some molecules act remarkably like benzene, where they have a huge amount of aromatic stabilization. Some you get a little bit of a bump, but not a lot of a bump. So I wouldn't say this is flat across the board true, but we do know that when we have an aromatic molecule, it's more stable than you would necessarily expect. Yep.
Does it have to do with how many, like, conjugations?
Yeah, absolutely. That conjugation provides a huge amount of stabilization. That and factoring it into a ring system provides even more.
So, like, some of the big ACs would just be super crazy stable.
Yes, unless they get too big, and that's a completely different story for another day. All right, so that's where we're going to stop today. Tomorrow when we come back, we'll look at this in terms of the orbital view.